So today we're going to talk about feedback transconductance amplifiers. And if we have time, we might get into feedback resistance amplifiers or feedback current amplifiers today as well. So we're going to start with our ideal case where our signal resistance R sig is equal to 0 ohms and our load resistance RL is infinitely large or an open circuit. And for this particular configuration, we are going to have our feedback network connected in series with the output of our open loop amplifier and the input of our open loop amplifier. And so we'll have something that looks a bit like this. So here in the middle, we have our open loop. Amplifier circuit where this is our signal VI, this is our current II, and down here at the bottom we're going to have our feedback network. What's the question, Bailey? Yes. Capital I, lowercase I. No, so that's the current flowing into the input terminal of our open loop amplifier. Here's our feedback network. So, and as I mentioned a moment ago, we're going to connect things in series. So here's our series connection. And our output port, looking in through here, is where we'll see our output resistance with feedback. Here is our output current, I out. On the left-hand side, we have our series connection as well. This is our feedback voltage. There we go. All right, so by inspection, we can see that I out is equal to simply A times VI. So effectively, in the ideal case, all of the current that's being supplied by that dependent source, AVI, is going to flow through that short circuit and bypass the output resistance R naught of the open loop amplifier. And so this is A VS minus VF, or A times VS minus K out. And rearranging, we have I out times 1 plus KA is equal to A VS, and therefore our gain with feedback AF should be I out over VS in this case. Looks like A over 1 plus KA, so we do have a negative feedback amplifier. In order to determine our input resistance with feedback, so that would be this quantity here, RIF, we're going to look at our input loop. So we will have VI is going to be equal to VS minus VF, or VS minus K I out, or VS minus K A VI. From this, we can see that VI times 1 plus KA is equal to VS, and therefore VI is equal to VS over 1 plus KA. Our input current II is VI over RI, or VS over 1 plus KA times RI. And from this, our input resistance with feedback RIF, VS over II becomes 1 plus KA times RI. So our series connection boosts our input impedance, effectively behaves the exact same way as the series connection did for our feedback voltage amplifiers. To determine our output resistance with feedback, we are going to set VS equal to 0 and apply a test voltage between the output terminals. So in the case where this guy is 0 and we place a test voltage here, applying Kirchhoff's current law, we can see easily that IX is equal to I out. which is A times VI plus Vx over R naught, right? So with a voltage source there at the output, our current I out split, some portion of it flows here. There is a potential difference over this resistor R naught now, so we have to take that into account as well. So let's see. With Vs equal to 0, Vi is negative Vf, so that's going to look like A times negative Vf plus Vx over R naught. And in this case, since Ix is equal to I out, Vf is simply negative Kix. All right, so what I'm getting at here, sorry, tripping over this chair over and over again. Right, so Ix is equal to I out by inspection. So that means we have a voltage of K times Ix here. Well, this is the same polarity as Vf. So we can replace Vf with Kix. So that's A times negative Kix plus Vx over R naught. And rearranging, we find Ix times 1 plus Ka is equal to Vx over R naught. And therefore, our output resistance with feedback, ROF, Vx over Ix, is RO times 1 plus Ka. So the series connection boosts on the output side as well. So for this type of amplifier, we're going to see that our input resistance gets scaled up by a factor of 1 plus Ka, and our output resistance gets scaled up by that same factor of 1 plus Ka. All right, so this is how the ideal case behaves. For the practical case, we really only need to figure out how we need to look at our feedback network in order to apply what's going to happen, okay? So, since our feedback network is placed in series on both the input terminal and the output terminal, so let's write this down here. Practical case. We have our feedback network. I'm going to make this smaller actually. On the left-hand side is port 1, as per usual. On the right-hand side is port 2. We find R11 by looking into port 1 with 2 open circuits. We find R22 by looking into port 2 port 1 open circuit. Okay, so this is slightly different, and it's because we have a different feedback connection, right? So when we had our feedback connection in parallel on the output side of the amplifier, I know this gets confusing because port 2 is considered the input side of the feedback network. But anyway, so when we had the parallel connection on the right-hand side, and we looked in through port 1, we needed to short circuit this term. Whenever we have a series connection, we're going to leave it open circuit. We're doing the exact same thing the other way around. Okay. To determine our feedback factor K, we take our feedback network, we apply current source on the right-hand side, we measure the voltage on the left-hand side across an open circuit pair of terminals such that this current, the current I flowing into port 1 is 0, and our feedback factor K is equal to VF over I out, and I1 is equal to 0. Once we've determined R11, R22, and K, we can proceed along with our analysis effectively exactly the same way that we've done previously. So with that in mind, let's jump ahead to an example problem. So let's look at the following circuit. Call this transistor M1, this transistor M2, this resistor RF, let's call this VN, and this is our output current I out, and I'm going to label these little X's right here. I'll explain what they mean momentarily. This is where we're going to measure our output resistance with feedback. Looking in through here is where we're going to measure our input resistance with feedback. This is our signal VI. This is our signal VF. This is up here. This VD. So, Luke. We are going to take into effect channel length modulation for this particular example, sure, but it's on a case by case basis, depending on whether or not I tell you to do it, kind of. The practical case is effectively, we don't have to worry about any signal resistance. We don't have to worry about any load resistance. And we assume that the feedback network does not load the system. Or excuse me, that's the ideal case. For the practical case, we're saying all of those things are a possibility. So the practical case representation is really what's going on when, for the most part, the feedback network and any signal resistance and any load resistance loads our open loop circuit. So, all right. So we can think of this as a bit of a two-stage amplifier circuit, where on the left-hand side, we have some sort of common gate amplifier. And on the right-hand side, we have some sort of common drain or source follower amplifier, where we've also got this feedback network that's linking this node to the gate of transistor M1. Okay. So what's our feedback network look like in this case? So here's port 1. Here's port 2. The bottom node, as always, is ground.
Output voltage, or are we taking the current our output for this?
So this is a transconductance amplifier, so the output signal is that output current. So the goal of this amplifier is to convert some input signal at the source of transistor M1 into some sort of drain current in transistor M2 that in turn drives some load, like a laser diode or something like that, where the intensity would increase as I out gets larger. We could, if we were so inclined, define an output voltage as well that would allow us to measure something, but because this is a transconductance amplifier, I'm trying to make it less confusing by not including an output voltage measurement point, because it doesn't particularly matter. That's just a way for us to, we would use some sort of resistor or resistor network to convert that output current into something that we could measure with a scope. But that would be an extra sense network that would slightly mess with our analysis. So I'm just trying to make it as bare bones as possible here. All right. So our output current I out here, our drain current, all of it flows through M2, all of it flows through RL. And then, so this is where things get a little wonky here, but we know that our output current is going to flow through our feedback resistor RF, which is in turn going to influence our signal VI, right? So we can treat this point right here as our output, but it's also connected to our input. So what I know that this is God knows, now is not the time to update Java. Sorry. So effectively what we're going to have here is a short circuit between the output and the input, right? All of the current is flowing through our load resistor here, and then it's all going to continue to flow through here. So this is our output path, or the current that the path that our output current is taking is just straight to ground. So we have a path from this point to our input. So we have a short circuit, and we also have from this point to ground our resistor RF. Our feedback network is literally the resistor RF. So R11, if we look into port 1 with port 2 open circuited, what do we see? RF. For R22, if we look into port 2 with port 1 open circuited, what do we see? RF. For K, if we apply a current source on the right-hand side and measure the voltage drop on the left-hand side, we're going to see that VF is equal to I out times RF. Well, VF over I out is RF. So K is also RF. So the single resistor is everything to our feedback network. It's how it loads the input side, it's how it loads the output side, and it contributes our feedback back. It should make sense, at least from this perspective. We have an input current and an output voltage, which means that our gain should be a transconductance. And so our feedback factor needs to be a resistance to have 1 plus Ka equal a number. All right, so from here, we look at our open loop circuit. So here's our resistor RD. Here's VDD. And then on this path, we're going to see RL. In series with R22, which is just RF. On the left-hand side, here's VN. And then here's RF. Here's our output current. Where we're going to measure RO. Here's where we're going to measure, determine RI. Okay. So what I'm going to do is I'm going to split this up into two circuits. Okay. Where this voltage Vx serves as the output of the left-hand portion, and it serves as the input of the right-hand portion. Okay. If we are including the effects of channel length modulation for transistors M1 and M2, I'm not sure if we covered what a common gate amplifier looks like with channel length modulation effects included. So we'll spend a minute here and analyze that circuit. Okay. So for our left-hand circuit, we have something like this. I'm just going to write this down. Common gate Here's our gate terminal. That's the gate of transistor M1. Here's VGS1. Here's the source of transistor M1, and this is where we're applying our input signal. Vin. Here we have GM1, VGS1 in parallel with R01. In our drain terminal and ground, we see resistor RD. And that drain node is also where we take our output voltage, Vx. So does this look reasonably like what the left-hand stage should appear as, with channel length modulation included? All right, so if we apply Kirchhoff's current law at node D1, what we're going to have is Vx over Rd plus Vx minus Vn over R01 plus GM1 times VGS1. Now, how can I relate VGS1 to Vn? Equal and opposite, right? Is equal to 0. From this, let's go to the next page here. I have a factor of 1 over R0 plus GM times Vn is equal to a factor of 1 over Rd plus 1 over, sorry, these should be R01s and GM1s. Did I remember to do that over here? I did, okay. Times Vx. And from this, I can see that Vx over Vn is equal to 1 over R01 plus GM1 divided by 1 over R01 plus 1 over Rd. And just to make this a little less annoying, I'm going to multiply by R01 over R01, giving me 1 plus GM1 R01 over 1 plus R01 over Rd. So that's my voltage amplifier stage. Now let's look up here what's going on our second stage. Right? So I have my input signal Vx. I have my source tied directly to ground. And then I have this RL and this RF here in series. Sorry, I said source tied directly to ground, but it should be drain tied directly to ground. I'm going to lump these two guys together and just call it a single resistance RS for bookkeeping's sake right now. Okay, where RS is just going to be equal to RL plus RF. So my second stage calling this my follower stage, and I'm putting follower in quotation marks because the source follower is a voltage amplifier, and that is not what we have here, right? We're converting our input voltage into a current. Is going to look something like this. So at the gate, we have our signal Vx. At our source, we have those lumped together resistors I'm calling RS. And then between the drain and the source, we have GM2, VGS2. Here is R02. And then here is my current. IF. Flowing into my drain terminal of my transistor. It also happens to flow through my resistance RS as well. So does this look like what my small signal model for the right-hand side of the circuit should look like? Let's start there. All right. So what I'm going to do to solve for I out here is I'm going to apply current division. And so what I mean by that specifically is I have this current provided by this dependent source, GM VGS2. And it has an opportunity, some part of it will branch off and flow through RS to ground. Some part of it will branch off and flow through R02 to ground. So this current sees these two resistors as effectively in parallel. All right. So I out is the current that flows through the resistance RS, right? It's flowing in from the power supply voltage, branching off, recombining, and flowing down through here. So using current division, I can say that I out is equal to GM2 times VGS2. Let's talk about what VGS2 is going to be. The voltage at my gate is Vx. The voltage at my source is I out times RS. So VGS is VX minus R out times IS. RS I out. So that's my GM VGS part. Now I have to use my current division relationship, right? Since there are only two resistors here, I'm going to use the current division equation for only having two things, which is the path I don't want divided by the sum of the parallel paths, right? So that'll be R naught 2 over R naught 2 plus RS. And now it's just algebra time, right? So this is going to look like I out plus I out times GM2 RS times R naught 2 over R naught 2 plus RS. On the right hand side, I'm going to have VX times GM2 R naught 2 R naught 2 plus RS. And let's see here. So I'm going to call this I out times 1 plus GM2. So I have RS multiplied by R naught 2 divided by RS plus R naught 2. That's just RS in parallel with R naught 2. And from here, I out over the X looks like GM R naught 2 over R naught 2 plus RS divided by 1 plus, sorry, this GM here should be GM2. I apologize for forgetting my subscript. 1 plus GM2 R naught 2 in parallel with RS. From this, our open loop voltage gain A is simply I out over Vx multiplied by Vx over Vn. One plus GM2 R naught, sorry, mixing myself up here. GM1 R naught 1 over 1 plus R naught 1 over RD times GM2 R02 over R02 plus RS divided by 1 plus GM2 R02 in parallel with RS. Literally multiply those two things together. There may be simplifications that can be made. I'm not entirely sure if that's true, so I'm just going to leave it like this. Luke, what's up? One plus R01 over RD. Yes. So if we scroll up here, from this guy, right? So our first gain stage multiplied by our second gain stage. Yes. Sure. So I don't know that we're actually seeing them in parallel, but mathematically they appear in parallel because here we have a factor of RS times R02 over RS plus R02, which mathematically is the exact same thing as R02 in parallel with RS. Yeah. So them physically appearing in parallel, yeah. Mathematically, to make it less horrifying to write down over and over again, let's go with that route.
I like it simple.
Yeah. Race.
So is there any issue with treating it as a source follower fire? Over RS?
So there is a little bit of a problem there. And what I mean by that specifically is that if we were treating this as a source follower amplifier, our output node would be here, right? With our output node here, our feedback network would see this load resistance, which isn't technically needed for a source follower amplifier since we could bias it with a current source. But our feedback network would be the resistor RL up here, and then the resistor RF in that vertical configuration. Another potential problem that we would see there is determining our it's no longer a transconductance amplifier. B, we would be looking into this terminal with regards to what we see as our output resistance, as opposed to looking in up here. So I honestly don't know exactly like what the fallout of those manipulations would come out to be. We're looking in at different places to determine slightly different things. But I can definitely see a reason why you would want to treat it as the other one, because it's a lot easier to analyze. Yeah. So I don't have a really good answer for your question other than we need an example of transconductance, so I'm making this behave like a transconductance amplifier. Yeah. Okay, so are we reasonably in accord on our open loop gain calculation? All right. So now let's talk about how we're going to calculate our input resistance. Okay. So our input resistance is effectively us looking at this circuit and then dividing this input voltage by the amount of current that's popping out of that terminal. So we're looking in through the source and effectively trying to see what falls out. Now, if my gate and my drain were tied together, that would make this trivial, but they are not. So I'm gonna take a snapshot of this and we're gonna play around with it. All right, and let's call this RI calculation. Okay, so here's VN. Here's our current IN. And I would argue that this is also our current IN. Because if this current splits up, it's going to recombine and flow down through the resistor RD. Does that seem like a reasonable-ish observation there? All right, so my goal here is to try to relate VN and IN, and I'm going to attempt to do this using Kirchhoff's voltage law. And so what I mean by that specifically is that I have a voltage drop over my resistor RD that is equal to IN times RD has to be the voltage drop over this resistor R01 plus this voltage VN. Does that make sense? So the potential difference between here and here is this drop plus this drop. All right, so the voltage drop over resistor R01 is going to be R0, I don't know why I wrote 2 when I literally just said R01, R01 times the current flowing through R01. Well, I can call the current flowing through R01 IN plus GM1 VGS1, and that's the current flowing into the negative polarity terminal. So I'm going to have negative IN plus GM1, and VGS1 is still negative VN. And then I will add to this VN like so. Is my KVL equation okay? Anybody see anything that's looking wonky or weird to them? One of the reasons that I'm asking is because I didn't quite have time to finish this part of the problem when I was working on it earlier. So I want to make sure I'm not making a mistake. All right, so from here, it's just algebra fun times, right? So we have a factor of R01 times IN that we can move to the left-hand side. And then on the right-hand side, we're going to have VN plus GM1 R01 VN. Did I screw something up? So INRD is equal to this drop plus this drop. This drop is R01 times the current flowing in, which is IN plus this guy, but it's flowing into the negative polarity terminal, which is why I included this negative sign here. And then I add to that this specific drop. So I'm feeling pretty damn solid about this guy right here. Did I make a mistake moving stuff around on the second bit? That is possible. Julia is shaking her head no. So let's just double check it, just because I don't trust me, not I don't trust Julia. So the INRD on the left-hand side stayed on the left-hand side, so nothing happened there. We have IN times R naught 1 and a negative sign. We move it to the other side. It gives us positive IN times R naught 1. We have negative R naught 1 times negative VN times GM1 on the right-hand side, which is where this GM1 R naught 1 VN comes from. So I feel like that's pretty legit. And then we have this VN all by itself. I would be hard pressed to mess that part up with just leaving it the hell alone. So I feel like I got that part pretty right. Now, I also feel pretty okay with this because it looks familiar to me from something that we did in 335, which always makes me feel better about when I derive things. So I see IN times R naught 1 plus RD on the left-hand side. I see VN times 1 plus GM1 R naught 1 on the right-hand side. So RI should be VN over IN, which should look like R naught 1 plus RD over 1 plus GM1 R naught 1, if I've done my algebraic moving crap around correctly on this point, right? So I'm moving this guy over here, so I'm leaving that alone in the numerator and then pulling that guy over there. All right, so that's my input resistance without feedback. And then that would be boosted by my amount of feedback for our closed loop configuration. Now let's talk about measuring the output resistance. And this is where things are a little bit difficult than we would normally consider because this is our first time ever actually considering what's happening when we have an output current. Because everything to this point has always been with respect to output voltages, right? So I've chosen these breakpoints here. So the reason why, so let's talk methodologically, maybe that's a word, about what's going on here, okay? My output current here is my drain current because the job of a transistor is to convert an input voltage into an output current. And for a MOSFET, that is taking some voltage VGS and turning it into some current ID. So I specifically am calling my drain current the current flowing through my drain, all right? I out. What I'm going to do here is I'm going to break my feedback loop open, or break this loop open. And effectively, this would be the same as me placing a test voltage source in here where I've broken things and seeing what that test voltage source would be, or what that test voltage source sees with Vn is equal to 0. Another way to think about that is, what does my output current I out see looking up in series with what my output current sees looking down with Vn shorted out? So looking up is pretty trivial, is a short circuit. Looking down is potentially a little bit more difficult, all right? So let's think our way through things real quick here. If Vn is shorted out to ground, what does Vx have to be? 0, right? Because if I don't supply an input signal, I don't get an output signal for this voltage amplifier, that first stage, okay? So I'm looking at a situation to where I'm looking into the drain with my gate terminal shorted, and then I have some resistance looking down. So effectively, I'm looking at the output resistance of almost like a common source amplifier that has some sort of source degeneration. We can actually prove that pretty easily, okay? So Calculating R out. My gate terminal is grounded. So this is G2. Here's VGS2. Here is that source resistance RS. Here is GM2. VGS2. Here is R02. And then this is where I broke into the circuit to apply my voltage source. All right, so hopefully we can all see. This is also my current IX. And so if I apply a Kirchhoff's voltage law equation here, this is going to look exactly like it did when we were looking at emitter and source degeneration. I'm going to have Vx is equal to the voltage drop over resistor R02. So it's going to be R02 times Ix minus GM2 VGS2, where in this case, VGS2 is negative IXRS. Plus the voltage drop over RS, which is IXRS, and my output resistance R0 is going to be Vx over Ix. So that's going to look like RS plus R02 plus GM2 RS R02. Or exactly what I said earlier, our output resistance R02 degenerated by that resistance RS. And at this point, we have everything that we would need in order to throw it into our blah, blah, blah with feedback equations. So that is a feedback transconductance amplifier circuit. We only have 10 minutes left of class. So what I will need to do for Wednesday is cover feedback current and feedback transresistance, and make sure I have 2 examples short enough that we can finish in the class period time. Or worst case scenario, I just write out the full examples and then give you guys those to look at. But for the most part, we've covered everything that we would possibly need to figure out what's going on now that we've had an output current that we need to figure out how that behaves. Because everything else is literally the exact same things we've done. I think the only thing we haven't seen yet is if we have a parallel connection on the input side as to how to treat that feedback. So anyway, that's enough out of me for today. I will see you all on, yes.
And whenever you were going over the right-hand side circuit, why were you considering that a source follower instead of a common emitter or common, what is it?
So I
Source.
technically wasn't considering it a source follower because for a source follower amplifier, that would have meant that we would have been taking the output voltage at our source terminal. It's not a common source amplifier though, because for a common source amplifier, we would see a resistance between the drain and ground, and instead we had a short circuit there. Technically, this wouldn't be considered a common source, a common gate, or a common drain amplifier because it's not a voltage amplifier, and all of those amplifiers work, right? This is a transconductance amplifier in as much as it's converting that input voltage Vx into an output current I out. The topology to me just looked the most similar to a source follower, which is why I called it a quotation follower stage.
Okay, I was just confused because I was looking at input was at the gate and then the output looked like it was being taken from the drain. That's why I was confused.
Right, yeah, but because it's not a voltage amplifier is why I wouldn't consider it to be a common source amplifier. Because the common source amplifier, you're 100% correct, in a common source amplifier, we apply the input voltage at the gate and we measure the output voltage at the drain. But because this isn't a voltage amplifier, I was just trying to figure out something that it looked the closest to, and to me, that would be a source follower.
Okay, no, that makes sense.
All righty, anything else? All right, see you guys on Wednesday.